Hi everyone. So in this video I will be providing a very simple beginner friendly solution to the problem B of contest 976 of Codeforces. So the problem name is brightness begins, right? And it's a pretty much simple problem statement. We have provided with n light bulbs and they are numbered 1 to n, and it is said that initially all these light bulbs are on, right? And for it, like, this is the operation which we are going to perform, right? For each of 1 to n, we are going to flip the bulb. Let's say we are going to flip all the bulb j such that j is divisible by I. I will be providing an example for that for better understanding, right? And after performing all these operations, there will be several bulbs left which are still on, and our goal is to make this number exactly k. And the problem is a little reverse. We are basically provided with k and we want to find the minimum number of n such that this scenario happens, right? Now it's a bit tricky here, and I will provide an example for better understanding. So let's say if for initial case, let's say your number of bulb is 5 and I am representing 1 for on and 0 for off, right? And initially it is said that all bulb are on, so I will write 1 1 1 1. Let's do some more spacing here, right? Initially all of these 5 bulbs are on, right? Now I have to perform this operation. For each I 1 to n, I will flip all the bulb j which are divisible by I, right? So let's begin with 1, of course, with the index 1. So our I is 1, right? And 1 can divide all of these index, like 1 can divide 1 itself, 2, index number 3, index number 4, index number 5. So for I equals to 1, our bulb will be turned off, right? All of these will be flipped to off, right? For I should write here like for I1, right? Our outcome will be this. Now for I equals to 2, now I'm picking this index. Now we have to flip the indexes which this 2 can divide, right? 2 can divide itself, right? 2 can divide index number 4, and now 2 can divide 6, but 6 is not there. We are only having 5 bulb, right? So this will remain 0, and now 2 can divide itself, so this will become 1. Now this will become 0, this will become 1, this will become 0. I mean, this will stay 0, right? And similarly we can go on. Now I will pick I equals to 3, so 3 is this. 3 can divide itself and there is nothing more 3 can do, so it will be 0 and 1. Now this third index will be flipped, it will become 1, and this will remain 1, and this will remain 0, right? Similarly for I equals to 4, only fourth index can divide itself and there is nothing more. Similarly this will be 0 1 1, and it can flip itself, right? And now this will be 0. And similarly for I equals to 5, we can only flip this one because 5 can only divide itself, so this will become 0 1 1 0 and 1. So finally we have this. Finally for n equals to 5, we will be left with 3 number of on bulb, right? Yeah. So the problem statement is, I think, pretty much clear, and I should see, is there an example? Okay, so round is finished. Is there example of 5? Yeah. So you can see there, if the n is 5, the k is coming out to be 3, right? Yeah. So first we should observe, like, what is this problem demanding here. So every time, what, let's say if I pick some index, some jth index, right? So jth index is initially initially it is on, initially its value is 1, right? Now this can be flipped multiple number of times. Basically, let's say if this thing is flipped, let's say even number of times, right, then it will remain on, right? This thing will remain on. Let me just check the problem statement. Yeah, yeah. So like if I pick some jth index and initially its value is 1, initially it's on, and if this thing is flipped even number of times, then it will remain on, right? So basically we have to find that how many index are there which are flipped even number of times. Other are flipped odd numbers of time, their value will become 0, right? So basically, when an index is flipped, it means that it is divided by some other index, right? When let's say if I have array here, and if I have some I, and then if I have some j, and if this I can divide j, and it leaves the remainder 0, then we say that yes, the j is flipped by this I. And basically this has to be done even number of time. Let's say if you pick some index, now I want to give some real example. Let's say if you pick some index, let's say 5. Now 5 is a prime number, right? Only 1 can divide 1 and 5 can divide them, right? 1 and the 5 itself. So this particular number will be like the operation of flipping will be applied even number of times. So whatever the value will be at 5, it will remain the same, and initially it is on, so it will remain on, right? So our goal is to find how many indices are there which are flipped odd number of times. So if I take one example, let's say if there is some index 4, right, and how many numbers can divide it? 1 can divide 4, 2 can divide 4, and 4 itself can divide 4, right? Now this 4 is basically flipped odd number of times, and its final value will become 0, so it basically turned off. And this is what we have to find, right? So how many indices are there which will be eventually turned off, because our k value will be n minus number of bulb which will off eventually, right? And how many number of bulb will be off? These are the number of I will write it here, number of bulb off, basically numbers between 1, 2 and which are divided odd number of times. I think this is pretty much clear now, right? Now we have to make one observation here. Let's say you pick some series 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I want you to make some observation here. Let's say if you pick 9 is a perfect square number. So 9 is made from 3 into 3. So how many factors can you make for 9, right? You can only make 1. I will write here factors for 9. You can make 1, you can make 3, you can make 9 itself. So there are only 3 which are odd number of factors, right? Let's say if I pick another perfect square number, if you pick 4, then it is made up of 2 into 2, right? And how many factors are possible for 4? It is 1, 2 and 4 itself, right? This is also odd number of factor. Let's say if you pick any perfect square, let's say if I pick 36, how many factors? 36 is made up of course 6 into 6, and we want to see how many factors are possible for 36. So let's say Start with greater to smaller. 36 itself can divide it, 18 can divide 36, and then 12 can divide 36, 6 can divide 36, and 3 can divide 36, 2 can divide 36, 1 can divide 36. So there are 1 2 3 4 5 6 7 number of factors. So every time you can also prove this mathematically, that every time if a number is a perfect square, it will have odd number of factors, right? So our problem statement is now very much simple now, because we only have to find this number of bulb of. Now number of bulb of was equals to number of bulb between 1 to n which are divided odd number of time, basically which have odd number of factor. Basically now our problem statement is pretty much simple. We just have to find number between 1 to n which are a perfect square, So this is pretty much simple now. Our problem statement is coming out to be breaking down to be very much simple now, right? And how do you find number of perfect square? It's pretty much similar. It's pretty much simple. Let's say if you have any number, let's say 81, how will you find it? How many perfect square between 1 to 81? How will you find this? If you wanted to find how many perfect square between 1 to 81, you can see that 81 is a perfect square of 9, right? So if the perfect square of 9 is 81, then obviously every number smaller than 9 will have their perfect square between 1 to 81. This is like pretty much basic. And let's say if our number is 90 and you do square root of 90, and it's not a whole number, right? It is 9 point something, I'm not sure what is, but 9 point something, right? So if you floor it down to a whole number, you will get 9, right? And how many perfect square between 1 to 90? This is basically 9, because you see 9's square is 81 and 81 is smaller than 90, and every number which is smaller than 9, they are bound to have their perfect square smaller than 90, right? So so what we encountered here, number of perfect square between 1 to n will be square root of n, and more specifically you can floor it down, right? So our problem statement is now very much clear. We know number of perfect square between 1 to n is the floor of this, and we have to find the number of bulb of, which is the number of perfect square between 1 to n, and sorry, we have reduced down to this. We have to find the number of bulb of, which is number of perfect square between 1 to n, and that thing is floor of square root of 9. So I will reduce this problem statement. I will just copy this thing, I will paste it here, and now we have reduced our problem statement to number of bulb of is floor of square root of n, right? So I will just put this value here, and this is our mathematical equation. K equals to n minus square root of n. Now it's a very straightforward solution for you guys, because let's say if you are provided with n, you can find k, and similarly in the initial of this problem you are provided with k. Now you can find this n, because you can solve this quadratic equation. Now either from this point you can solve it using using quadratic formula you can solve it by this way, and there is one more way, you can also solve it by binary search, right? Because every time you pick the value, you have the initial value. Let's say if you initialize our left bound with n, and sorry, if you initialize your left bound with k, and your right bound with the maximum possible number, maximum possible long, right? Your answer of n will lie between it, and you can just iterate you can search binarily, and every time you can see that this condition is true or not, right? Now I will come back to my code, and like from this point I will suggest you guys to code yourself, because now you can also make a binary search solution from here, and also you can make a mathematical solution from here, right? And I will show you my code. So for simplicity I have created a binary search solution. Yeah, so this is my boilerplate, nothing. I have just taken input of k, and I have a maximum bound. You can make this anything else also. You just something significantly greater than 10 raised to the power 18, right? I can also make all these 0, and I can maybe I can try this, right? I'll make this 2 and 18, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So let's say I kept this as my max bound, right? I can initialize my left bound with this, left bound with k itself, because obviously my n is gonna be greater than k, right? And my right bound with this max, right? And I'm initializing my answer with a right bound, and I will just search it binary. Like, this is a basic template of binary search, and the key thing is creating this check function here. Every time you check for the mid, if this mid is a correct possible answer, you initialize it with mid and you reduce the range, right? And what happened in this check function, we have already shown you. In this check function, we basically just check the square root of our number minus this number itself. So this is the number of bulb. If this is greater or equals to k, then we will just reduce our range, and this range is gonna be reduced. Now we are basically reducing the range here, and this range is gonna be reduced until our number of bulb off is equals to k, and at that time we will be having our minimum number of n, and we will simply output this solution, right? So I will suggest you guys to code yourself, and maybe I can try to run this one. Yeah, so if we have the test cases here, I'll just run this one. So yeah, and this is also accepted solution. I will suggest you guys to try this binary search solution first, and also the more better solution is the mathematical one, where you can simply just compute this thing. And I know, like, you guys can compute this using the basic formula that was minus b plus minus sqrt of b square minus 4ac, and this whole is divided by it was 2b, I think, I'm not sure. So this is the elementary formula for that, solving the quadratic equation. You can also solve from that point. So yeah, that was it.